In 2009, Scott Taylor revisits his 1998 Easter Island paper. He has two objectives: addressing the weaker points of the model and also applying it to environmental crises of the present and of the future, especially the climate crisis. Even though his 1998 paper with James Brander was very influential, they were still criticized for some weaker points. First, the model seems to settle quite quickly on the sustained island steady state, without actually any dramatic disappearance of the forest, so without major catastrophe. This is a weaker point since we did observe that the forest was gone on the island. Second, of course, there is the absence of institutions, the apparent foolishness of the islanders cutting down the last tree without even reflecting on what they were doing. So the first thing he does is to define the concept of crisis precisely. So for him, environmental crisis is a dramatic, unexpected, and irreversible worsening of the environment that leads to a significant welfare loss. So this means it does not include things such as the slow and gradual loss of the number of species worldwide, or not really the gradual reduction in the world fish stocks. So these are, of course, very important questions, not just crises as he means them in his concept. So he demonstrates that to get a crisis, so in addition to the starting point of the Lotka-Volterra predator-prey model, he also needs three additional ingredients. First, a tipping point in the resource stock. So this is a threshold under which if the resource dips below this threshold, then it can't recover, even if conditions improve somehow. Then he also needs weak governance. So that is that extractions need to be close to free entry level, so not socially optimal. And finally, he needs positive feedback loop. So in the Lotka-Volterra model, the dynamics has a negative feedback loop between predators and prey that makes it virtually impossible for any population to crash. Since when one species is close to extinction, then the dynamic of the other always helps it recover in some way. So for instance, if the preys become very low, then the predators starve and their population becomes low as well, so then the prey can recover. But what he does is he adds positive feedback loops that can actually make a bad situation even worse, and in that case, crashes actually become much more likely. Adding a tipping point only requires a small modification to the natural growth. So he writes it as n of s, so n is the natural growth of the stock, equal to r that multiplies s minus t that multiplies 1 minus s over k, where t is the tipping point, and as before, r is the natural rate of growth of the stock, and s is the stock, and k is the carrying capacity of the ecosystem. So compared to this standard logistic growth, the only change is that reproduction, instead of being proportional to S, is now proportional to S minus T. So the intuition is that below this tipping point T, and even with a positive stock S, there is no longer a critical number of individuals to guarantee the survival of the species, and S does not increase and still declines inexorably. It's now time to ask some questions. First of all, how many steady state for S do we have in this system? So with no harvest. Pause the video and think about it. All right, so that's more tricky than it may look like. We actually have three steady states. First of all, when S equals K, that's easy. So because of course, when S equals K, S divided by K is 1. So 1 minus 1 is 0. We are at carrying capacity. So there's no growth in the natural stock of the resource. Second steady state, when S equals T. So in that case, the first parenthesis is 0. It means that we are just at the tipping point. So it means that we are just at the limit that makes the stock of nature essentially not grow. So that's why we stay there. And have you thought about what the third is? The third is when S equals 0. So what's tricky about this, of course, is that when S equals 0, actually, if you compute it, you get a growth rate that is negative because we get S minus T, which is just equal to minus T. But so what's happening there? Well, the thing to note is that, of course, the stock cannot be negative. So imagine you're at 0. So where can you go from there? Well, the growth is negative, so there's no way to increase, but there's also no way to decrease. So actually, the value of the growth at 0 is 0. Once we are there, there's just no way to gain anything else. So actually, any value of the stock between 0 and t leads to a crash, basically. Now, second question. Without harvesting still, how many stable steady states does the system have? So a stable steady state, S star, for instance, is stable if for values of S in the neighborhood of S star, then the system will evolve towards S star. So if we start at S star and we have a small deviation from it, then it goes naturally towards it. And of course, it's unstable if the system evolves away from S star. Pause the video, try to answer. Answer, we have two stable steady states, S equals K and S equals 0. So perhaps a better way to do it is to explain why T is not a stable steady state. Well, imagine we are slightly above T, so the system is exactly at T, and then I add some other individual in there. What happens? Well, now we have just enough to start the reproduction and start to increase the value of the stock. So S actually starts to increase, and by increasing, it gets away even more from T. And this goes on until we get to the other stable steady state, which is going to be at value K. And on the other hand, if, for instance, I'm exactly at T, and then one individual dies, then that's enough to make the growth of S actually negative, and if N of S is going to be negative, so the stock is going to be get even more negative, so even more away from T. So again, we're going away from T, and now in which direction are we going? Well, we're going towards the other stable steady state, which is towards 0. And of course, we can imagine that, for instance, if we are at 0, then if we increase a bit the stock, for some reason, if I introduce one fish in the lake, well, I just have to wait a few years, and that fish is just going to not do anything and eventually die, and the stock is going back to 0. So that's why we see that 0 is a stable steady state. And same thing for K. So if you want a trick to know whether some steady state is stable or not, so the only thing you have to do actually is compute its derivative, which is the derivative of the growth of the stock with respect to the value of the stock. And you estimate this at this steady state. And if this derivative is positive, then you know that it's an unstable steady state. And if the value is negative, the derivative is negative. So here it would be dn of SDS evaluated, for instance, at so if you evaluate it at t, then dn of SDS would be positive. Do it yourself. And so you know that it's an unstable steady state. So I'm going to leave it at that. So we can include some examples of why we would observe in nature tipping points. So one was already mentioned by de la Pérouse in his log of the trip to Easter Island. So what he's saying is, if there is soil erosion and wind, then if you have too few trees, then this makes it very difficult or impossible for the last remaining trees to survive. So this actually answers the rhetorical questions of Jared Diamond. Who cut down the last tree and what were they thinking when they did it? Well, nobody had to cut down the last tree. It's just that past some point, then actually nature itself would have just dealt the last blow. Or nature, in the case of Easter Island, was rats. So rats would have eaten the last trees and none would be left in Rapa Nui. Another obvious example of a tipping point would be lack of genetic diversity. So for instance, Trail and co-author in 2009 did survey the literature, and they found out that in many instances, if we don't have a few thousand mature individuals per species, then sometimes the species is not viable long term. So that's the importance of tipping points. Now we're going to go on and look at weed governance in the next video.